Está Julio. Hola Julio, ¿cómo estás? No se te escucha.
Ya, ahí.
Sí, ya te escucho.
Sí, ya.
No sé por qué, a ustedes no sé si les pasa, Zoom baja el volumen hasta 0. Entonces tengo que entrar a configuración y subirlo. Bueno, yo ocupo Linux Mint, entonces no sé si en Windows o en
Fedora no te pasa eso.
¿No?
No.
No, no.
Ah, ¿verdad?
Yo no me pasaba Fedora, ni aunque me pagara.
No. Pero fíjate
Dime.
que es bastante, digo, sí es una lata andarlo actualizando cada semestre, pero a mí me ha jalado bien.
Sí. Yo empecé a usar Linux hace como ya casi 20 años. Empecé con Red Hat 7.3. De ahí brinqué al 9. De ahí brinqué a Debian. De ahí brinqué a... El problema con Debian es que pues, los drivers luego están complicados. Y de ahí me fui viendo a Ubuntu, a Fedora, a CentOS. Me gustó mucho en algún momento OpenSUSE, distribución que es mucho de Europa. Y al final, cuando encontré Linux Mint, ahí me quedé. Creo llevo más años con Linux Mint que con mi esposa.
Eres más feliz, dices.
No voy a contestar eso.
Yo empecé con Mandrake, no sé si lo conociste.
Sí, fíjate que nunca lo usé, pero sí lo conocí.
Y lo convirtieron en Mandriva y ya lo descontinuaron.
Ya se perdió.
Sí, ya se perdió.
Sí.
Ay, ahora que me acuerdo, recording is in progress. Vamos a tener que editar esta parte del video. Pedro just joined as an attendee.
Okay.
Ajá, ok.
Let me promote the panelist. Pedro?
Just wait, because you remember it takes a couple of seconds.
Yes.
To change from attendee to panelist.
Okay. Well, Pedro, can you hear me?
No, he's still not here as a panelist, either as an attendee.
Oh my God. Let me see. Pedro. No, I didn't see Pedro.
Just wait, because, for example, in the list of panelists and in the Zoom platform, I can see Pedro as a panelist. Pedro? So then the next time joins should be joining as a panelist.
Okay.
Yeah.
Okay. Pedro, can you hear me?
Yeah.
Okay.
I can hear you.
Good. Okay, let's start. Well, let's begin. So, good afternoon, everyone. It's a pleasure to present to Dr. Pedro Ramirez Gonzalez from the Institute of Physics of the Autonomous University of the San Luis Potosí. And his presentation is titled Towards a Fundamental Description of the Essential Features of Glass Transition. So, go ahead, Pedro. Could you present it? Okay.
Okay, can you hear me, everyone?
Yes.
Okay, and can you see my screen?
Yes.
Yep.
Yes.
Okay, perfect. Okay, I want to start my presentation by thanking the organizers for accepting my contribution, and congratulations to all the organizers for this wonderful event. The outline of my talk is the following. First, I want to describe some features that characterize much of the glass formers. Then I want to describe our approach to these problems. And next, I will show you some open problems and finally a brief summary. The glass transition phenomena have an overwhelming literature and many points of view converge on the problem. However, many of the glass formers present a set of characteristics independently of the specific nature of these microscopic components. A short and for sure incomplete list of such essential features are the following. First, the dependence of the final glass state on the thermal history, the Kovacs signatures of glass transition, and finally, the dynamical heterogeneities in supercooled liquids near the glass transition temperature. These issues forms a sort of checklist for any theoretical approach to the glass transition problem. One of the most important observations in glass formation is that during measurement of thermodynamic properties near the glass transition temperature, for example, a specific volume or enthalpy, we can find a strong deviation from the equilibrium behavior. I mean, these values deviate from the corresponding values at the crystalline solid or the supercooled liquid, which are the equilibrium states of reference. As illustrated in the figure, where the red line differs from the blue line and the extrapolation of the white line. In addition, according with the standard knowledge of glass transition, in contrast with the equilibrium state, the overall properties of the glass depends on the preparation protocol. For instance, different cooling rates promotes glasses with different physical properties, as also is presented in the figure with the labels glass A and B. Other of the glass transition main features are the Kovacs signatures, which consist in a series of experiments where the structural recovery is proved. I mean, such experiments help to characterize the relaxation processes suffered by the system to the equilibrium state after thermal or mechanical perturbation. By direct measurement of the equilibrium of the evolution of the volume, enthalpy, or other thermodynamic quantities through the variable delta, which is defined on the screen, several important features of glass transition can be identified, namely the intrinsic isotherms, the asymmetry of approach, and the memory effect experiment. The intrinsic isotherms consist in measurement delta after a sudden temperature change. They demonstrate a non-exponential decay of a structural recovery and the shift in the equilibration time during an isothermal relaxation as the temperature of annealing approaches to the nominal glass transition temperature. The asymmetry of approach consists in follow two routes to the final state, one above the final temperature and another below it. The experiment shows the nonlinearity of the structural recovery. Finally, the memory effect experiment consists in perform a sudden cooling to a final temperature, but in the middle of the relaxation process, the system is subjected to a sudden warming to an intermediate state with temperature in between the initial and the final state. Such experiment shows the non-exponential behavior of the structural recovery and the dependence of the kinetics on the thermal history. The relevance of these observations lies in the fact that several glass formers presents them independently of its microscopic composition. One important point to highlight here is that the Kovacs signatures are also observed if we measure the so-called feed tip temperature. Such quantity is defined by comparing the time-dependent value of some thermodynamic property with the same value at equilibrium. For example, if I measure the specific volume at time t, obtaining the value B0, then I can search for the temperature in which the system has the same value B0 at equilibrium, let's say Tf. Thus, we can say that the non-equilibrium state at time t has a fictive temperature Tf. Please remember this quantity because I will return to it later. Dynamical heterogeneity is another essential feature of the disorder materials which emerged from experimental studies of viscous molecular liquids near the glass transition. In these systems, local relaxation is measured by mechanical or dielectric proofs, showing a wide range of non-exponential relaxation times. Indeed, using computer simulations to study supercooled liquids, we can observe that the density fluctuation expected in the fluid become observable near the glass transition temperature. In contrast with equilibrium liquids, where density fluctuation relax at inaccessible time scales, near glass transition, the relaxation time grows enough to be observed. Essentially, dynamical heterogeneity refers to the presence of different local mobility at different regions of the system, which is observed as an inhomogeneous local density inside the system. The essential features described in previous slides constitute a sort of checklist for the understanding of glassy dynamics. What we are making is to apply the non-equilibrium, self-consistent, generalized Langevin equation theory, the Nextlet theory, which is a formalist that I will briefly describe later, to achieve an overall and fundamental picture of these problems. Why is this goal important? Well, let me tell you that the standard approach of statistical thermodynamics are not able to capture any of the features described previously. Necessarily, we need to develop extensions of statistical mechanics where fluctuations are included in the description of the system. One of the most important attempts for developing a fluctuation theory is the Onsager-Matchloop theory of thermal fluctuations. However, such a theory is only useful for relaxation processes which are very close to equilibrium. So in order to have a good picture for the strong deviation from equilibrium observed near glass transition, we need to go beyond Onsager-Matchloop theory. Now, let me tell you how to make such extension. Making a great oversimplification of the theory, the Onsager-Matchloop theory uses a mathematical model of stochastic processes called Ornstein-Uhlenbeck processes, and the physical assumption that thermal fluctuations are described by such stochastic processes. What we have done is to extend the Ornstein-Uhlenbeck process to non-Markovian situations and use a similar assumption that thermal fluctuations are governed by such extended processes. I don't have enough time to go through all the details, but the interested people could see the paper that is in the screen. The previous formalism is general and could be applied to any relaxation process. Indeed, we applied this formalism to study the local density fluctuations in fluids. The result is the so-called non-equilibrium self-consistent generalized equation, the Nextlet theory, which allows the description of non-equilibrium fluids and their time-dependent properties. This theory contains two levels of description, one macroscopic for the local density average, and one time correlation function, which is something like a time-dependent radial distribution function or structure factor if we go to the Fourier space. The other level is microscopic in the sense that describes the relaxation of the local fluctuations of the liquid through a waiting time-dependent intermediate scattering function. The two levels are connected by the time-dependent mobility B of t, which is in the screen, which is obtained from the microscopic level and governs the macroscopic one. The most important characteristic of the Nextlet theory is that it's able to predict two kinds of stationary states as a result of a relaxation process. Consider the main equation of the time-dependent structure factor at the top of the screen. If we ask for the stationary solutions, two possibilities arise. If the bracket becomes zero, then we are at equilibrium. In contrast, if the time-dependent mobility goes to zero, then we obtain a non-equilibrated arrested stationary state, which can be identified with glassy states. The picture given by the theory is the following. Imagine the phase diagram of a system, then points in the plot are like houses in equilibrium land, right? Now I want to go from point P to Q, and then I need to depart from the plot and explore a set of non-equilibrium states. Of course, if everything goes well, I can land to the other equilibrium state. But if a dynamic arrest condition is found during the relaxation processes, I will get stuck in a non-equilibrium state. That means that with the next theory, we are able to describe arrested fluctuations and non-equilibrium stationary states. In order to show the predictions of the next theory, we choose a simple model of a fluid, a soft sphere model described by a truncated Lennard-Jones potential, for which our calculation of local mobility at equilibrium coincides very well with computer simulations. And actually, we can determine the region for which the mobility becomes zero, which is the green line in the last picture of the screen. Below this line, the fluid becomes arrested, forming a solid-like state. Then we can study the relaxation processes outside and inside the arrest region. As a first approximation to the dependence of the preparation protocol, we made a stepwise preparation protocol in which between each temperature, we solve the next equations. The cooling rate in the model is defined by the total number of steps and the duration in each step. What we found in this case is that when a cooling process is made above some critical temperature Tc, the system always finds the equilibrium state no matter the cooling rate. In contrast, when the system is cooled down below Tc, strong deviations from the supercooled liquid properties are found, and actually the system gets arrested in a stationary arrested state, which depends on the cooling rate. In the figure at the top, you can see the relaxation of the maximum of the time-dependent structure factor for different cooling processes. The inset show a zoom of the final state, and we can see that there are different final states for different processes. The dotted line in the inset is the expected equilibrium state. As you can see, the theory predicts a cooling rate dependence on the final arrested state. Now, we can present the information in a different way. If we can define chi of t as a response function associated with the inverse of the time-dependent structure factor, we can obtain the two plots at the bottom of the screen. In both, the dotted line is the equilibrium value of chi of t. The left plot presents results for fast cooling rates, and we observe that the deviation from equilibrium starts to appreciate above Tc. In contrast, at the right, we found that for slow cooling rates, the temperature for where the departure to equilibrium begins is observed at Tc. In consequence, Tc separates the states which actually equilibrates for ones which are not able to equilibrate. Regarding to the Kovac signatures, our first approach is the calculation of a model for the fictive temperature for the fundamental equations from the fundamental equations of Nextlet theory, which allows to compare with the experimental observation in colloidal glass formers. Our models share the same features at qualitative level and as shown in the figure at the right of the screen. Of course, we need to improve some things in order to get a more quantitative description. Regarding to the dynamic heterogeneity problem, we will start for a linearized version of the diffusion equation, for which the time-dependent mobility is included explicitly. As you remember, we are able to calculate this time-dependent mobility from the Nextlet theory. Then we consider a system which is divided in many small cells, each one with a local time-dependent density. So we focus in two adjacent cells and how a prepared fluctuation, I mean an initial condition with different density at each cell, relax to the final state after a cooling process. In the plots at the bottom of the screen, we present the density profile through the adjacent cells. Red lines describe the initial condition where one cell has a different density than the other cell. The blue line is the final stationary state after a cooling process. Actually, an horizontal final state means that the density is the same for both cells, which is expected for equilibrium states. In contrast, non-horizontal final states means arrested densities among cells. Therefore, dynamical heterogeneities are presented. We observe that the theory predicts that such dynamical heterogeneities depends on the cooling rate. Slow cooling rates promote a homogeneous density between cells, while fast cooling rates promote non-homogeneous final states. Just to finish, let me give you two main messages. The first one is that the preparation protocols dependence, the COVAS signatures, and heterogeneous dynamics are essential features of glassy dynamics. And the second one is that our first attempts show that the Nextlet theory is able to describe qualitatively such essential features of glass transition phenomena. And finally, I want to acknowledge the great work of Jonathan Lira Escobedo, because this talk is based on his work, and always in collaboration with Patricia Mendoza Mendez and Rodrigo Vélez. In addition, let me thank all the collaborators and the crew at the National Laboratory on Engineering of Non-Equilibrium Matter for all the work and the enthusiasm. And a big thank you for your attention.
Okay, thank you, Pedro, for your presentation. Nice to see you.
Nice to see you.
Now we continue with questions from the attendees or panelists. So please raise your hand if you have a question, please. So let me see. Or panelists, if you have a question, I don't know. Emilio? No.
Victor, Ivan has
Pavel. Okay.
hand.
Okay. Okay. Ivan first. Ivan. Okay.
Pedro, nice talk.
Thank you.
I have a question regarding one of your slides in which you were showing us a picture. I mean, perhaps 4 or 5 slides. Yeah, that one.
Yeah, okay.
And in that picture was obtained from simulations or from the theory?
That picture was obtained from theory, but it's just an illustrative picture. It's not the real results of the theory in some sense. It's just to illustrate the model. But the work was generated using just a random distribution of densities.
I see. And for example, you have also a slide in which you were showing us several decades, and I guess you had the structure function, which was I think arrested. I'm not sure.
Which one? This one?
Yeah, that one exactly.
Okay.
So that system corresponds to a system in which you have particles with repulsive interaction. Is that right?
Right. It's correct.
And how hard is, from a simulation point of view, to perform all these decades in a simulation in order to confirm this?
Okay, in simulation is a little bit hard because, you know, usually in simulations you can achieve more around, you know, 10 to 4 power 4 or something like that. But in some sense you can find quickly the stationary state. Probably you can find some features that can you tell you that the system is arrested. But in this case, it's hard to have a long time simulation. But there are some things that we can check with a shorter simulation. For example, the deviation from the equilibrium starts very early in the relaxation process. So we can monitor it some properties that deviates from equilibrium very fast.
I see. Thank you very much, Pedro, and nice talk.
Thank you, guys.
Okay, we have time for other questions. So, Dr. Pavel Castro Villarreal.
Thank you. Nice talk. I was wondering about one of your slides, Pedro.
Yes,
That
which
one
one?
when you describe briefly the non-equilibrium generalized Langevin equation. And my question is very simple. It's just in the case of when you consider heterogeneities, this equation for the scattering dynamical function generalize easily as just to replace the mobility factor with a mobility
Yeah.
dependence on the
Yeah.
Fourier mode? Or
Yeah, in some sense, yes, but we are using a sort of approximation. You know, these equations are constructed for homogeneous systems. So what we are assuming in the extension for non-homogeneous liquids is that in each cell you have an homogeneous liquid. So it's some kind of a local homogeneous approximation. In this sense, we can solve these equations for each cell, and all the information is connected by the diffusion equation, in which each v of t comes from the solution of these equations, but in each cell in a local manner. So it's some kind of approximation, but with that approximation, we can make this kind of extension of the theory.
so in the case of the heterogeneities, in this equation that you are showing for the concentration, all the interaction information of the particles is encoded in the mobility.
Right, yeah,
Okay.
yes.
Yeah. Okay. Thank you very much.
Yeah, thank you, Tim.
Okay, so someone else has a question? I think, okay. Idilio, please.
Bueno. Hi, Pedro.
Hi, Delio.
Pedro, I have a question. For example, from your result about the cooling rate dependence, some people talk about the Gaussman paradox. So, is there any comment between your results and the Gaussman paradox, or is there any relation?
It's a long discussion. It's about the Gaussian paradox. Essentially, as I understand that, this deviation from the equilibrium from the glass solves, in some sense, this Gaussian paradox, because if the system is relaxing to the equilibrium state, which is the supercooled liquid, then all the properties will have problems at zero temperature. So the glass, in some sense, solves the problem for the nature, of course, in the sense that separates from the supercooled liquid line. But I'm not sure that we can say that the theory captures all these features in some sense. That we are just showing is that we can describe these deviations from the equilibrium states, and that are due to arrested transitions, to dynamic arrest transitions. So I'm not sure if I solved your problem, but I'm not sure that we can solve this problem, this question right now.
Okay. Thank you.
Okay. Thank you, Pedro.
Thank you.
So we can move to the other presentation. Alexis Torres, can you hear me?
Yes, hello. Hello, everyone.
Okay. If you try to present.
Let me share my screen.
Okay, good.
Please let me know
Okay.
if you can see my screen.
Yes, I can see.
Okay.
Okay, good. Okay, for me, it's a pleasure to introduce to Dr. Alexis Torres Carvajal from, in Spanish, is Unidad Profesional Interdisciplinaria Ingeniería, Campus Tlaxcala. His presentation is titled A Comprehensive Molecular Dynamics Study. So go ahead, Dr. Alexis.
Thank you. First of all, let me thank to the organized committee for this event and let me the space to talk about this. Well, the outline of the talk is the following. I will talk about the gel formation, approaching the study with molecular dynamics, and finally using some relevant results of the generalized Langevin equation, the self-consistent generalized Langevin equation that Pedro has already talked about. Well, first of all, let me say that the interest of this study is to know the properties of that people call gels, and in general we know some definition of these kind of systems are understood like colloidal or polymerical system that doesn't flow because they form a network that spans all the system, so they can resist some mechanical stress, and in general they cannot move when they reach the gel state. But usually gels are defined in terms of the host medium and the physical mechanism that the network that finally defines the gel is formed. For example, there are hydrogels, organogels, where the solvent, where the colloids or polymers are immersed, are, for example, water or some organic medium. And in other case, when the network is formed, there are two main mechanisms that are called, for example, chemical gels, where the particles forms bonds or are bonded by a chemical reaction. So these bonds are unbreakable, but there are other systems that are which are we interested, called physical gels, where the bonds are formed by physical interaction, for example, the so-called van der Waals interactions. And in this case, these bonds can be broken if we change the conditions, the thermodynamic condition of the system. So the formation of gel is reversible in this kind of system. So we are interested in this kind of gels. To model these gels, we use interaction potentials that are attractive at short range, like the Lennard-Jones, here given in equation 1, and the Lennard-Jones with a Yukawa repulsive tail that is of low range. And in this sense, these promote the formation of these bonds that eventually, according to the thermodynamic condition of the systems, forms the network that finally we can establish that is a gel. So In the literature, we found many studies about these gels, and many of them are based primarily on system with pure attraction, with short attraction, and eventually, in the last couple of years, there are some studies that incorporates the repulsive part in the study of this kind of gels. In this sense, we take the pure attractive short-range attraction fluid as a reference. We determine its phase diagram in order to know where are the studies, where are the states, sorry, in which the system is above the phase coexistence. And in our simulations, we start with a thermodynamic condition far above the thermodynamic, the critical point. Then we perform a quench to a final temperature inside this temperature of the inside of the coexistent phase region of the linear zones, in order to see what happened with the structural properties and dynamical properties. So we explore several thermodynamic states for both models, and the results that we determine are basically structural and dynamical properties. It's well known that if the systems are quenched to a final temperature inside the binodal or spinodal region, the static structure factor exhibits a peak at low values of K, which magnitude is finite in the sense that the magnitude stops to increase, and this is indicative that some kind of preferential magnitude is seen in the system. We observe that both systems, the Lennard-Jones and the Lennard-Jones with Yukawa, exhibits the same features, but there is a subtle difference between them, because the first peak observed has different magnitudes in both fluids, even if the thermodynamic state is the same. I mean, the final temperature at which the system is cooling is the same, and the time observed is also the same. The final structures differs, although the qualitative behavior is the same. We also analyze for several thermodynamic conditions and observe a similar behavior. Of course, we are interested in that we call it asymptotic behavior, in the sense that we cannot do perform simulation with a very long times. So we determine the static structure factor in order to use this information in the self-consistent generalized Langevin equation to finally determine the arrest phase diagram. But we can observe in this scenario that depending on the thermodynamic states, the static structure factor exhibits a peak, or for example, in the case of the Lennard-Jones fluid, exhibits a peak, or this first peak tends to diverge, indicating that a full separation in the system. But in the case of the Lennard-Jones with Yukawa tail, we cannot observe this behavior. So this is the main feature that we call it the respective non-equilibrium roots and equilibrium roots. Since in the Lennard-Jones fluid, we can observe a full phase separation if the temperature is inside the binodal region. In contrast, since the Lennard-Jones with Yukawa tail, with the parameters used in this work, doesn't exhibit any phase coexistence, so we call this an equilibrium root, because at the end we observe an arrested state, but the conditions are different, since in one case we see a phase separation, an interrupted phase separation, and in the other case the system has not a phase coexistence, for instance. No. In this scenario, for example, we observe some snapshots of the system. In the case of a packing fraction or volume fraction or 0.1, we observe at certain temperature, for instance, a temperature of 0.35, a full phase separation here. But if we continue decreasing the temperature, we observe that the system, the Lennard-Jones, expands and forms a network that is very compact. In contrast, the Lennard-Jones Yukawa fluid doesn't form this kind of structure, this compact kind of structure, but also we observe some kind of formation, but at a very low temperature, in contrast with the Lennard-Jones. So we determine also the local order parameter in order to see what is the microstructure of this fluid, and we observe an interesting feature since the Lennard-Jones fluid change dramatically its behavior at certain temperature, in this case 0.35. But the Lennard-Jones Yukawa also exhibits such dramatic behavior, but is dependent on the thermodynamic states. For instance, this change happens or takes place at lower temperature if the density is lower, as if the density is increased, the threshold or the temperature value where this change occurs is changed. So in this case, we can observe a difference between the Lennard-Jones and the Lennard-Jones Yukawa tail at the microscopic level. No? Well, we also determine how the bonds, how the particles are close together and forms the structure by means of the bond correlation function. Sorry for that. That is defined as in equation 3, where n means which particles E and J are bonded, are separated by a distance that we define. If they are bonded, this n takes the value of 1. If they are unbonded, takes the value of 0. So we determine this correlation, and we found that, for instance, at low packing fractions, we see that the Lennard-Jones at low temperature exhibits an increasing formation of bonds, and the time that this bond lives is longer than in the case of the Lennard-Jones with Yukawa tail. So the first message here is the bond lifetime in the Lennard-Jones with Yukawa repulsion is less than in the case of the Lennard-Jones, and in the other case also here we can see that the number of bonds in both fluids are different. So this is related with the kind of structure that we see at the final states that we call it the asymptotic time. We determine other interesting properties, for example, related with the relaxation time. We determine self-intermittent scattering functions, and we also observe different behavior in both fluids. For instance, in the Lennard-Jones pure fluid, we observe that we reach non-ergodic states at temperatures near to 0.1, for instance. But in the case of the Lennard-Jones with the long repulsions, we observe that the system remains in ergodic states. So this is a difference between both fluids, although we consider other densities, we can recover the same behavior related with the non-ergodic states. We determine or we summarize all this information with the alpha relaxation time. We again observe a dramatic change for certain temperature, in this case near to 0.4 for the Lennard-Jones. But in the case of the Lennard-Jones with the Yukawa tail, we observe that this change takes place in different temperatures that almost depends, or we can assume that depends on the density of the system. So this information also is corroborated with the computation of the diffusion. First, we determine the mean square displacement, and also we confirm that we can already see that at high temperatures of this quench, the system remains in a fluid state. But if we decrease the temperature, we can observe that the mean square displacement dramatically decreases. And in the case of the Lennard-Jones, although we see this dramatically change, there is is it a lower temperatures than in the case of the pure Lennard-Jones system. This behavior is also seen for other densities, is similar. So we determine the diffusion coefficient, and again, we see this dramatically change for certain temperatures, independently of the density in the case of the Lennard-Jones fluid. But in the case of the Lennard-Jones fluids with Yukawa tail, we observe that this change of the diffusion coefficient takes place at different temperatures depending on the density of the system. We can assume, or we can trace this difference if we see the microscopic final structures. For instance, if the temperature is near to 0.45, that is the temperature above the critical point of the reference systems, both fluids remains in the fluid phase. But if we decrease the temperature, we observe that the Lennard-Jones fluid separate in phases, while the Lennard-Jones with Yukawa tail remains in a fluid state. If we further decrease the temperature, we observe now that the Lennard-Jones tends to form this kind of structure. Meanwhile, the Lennard-Jones with Yukawa remains in a fluid state. If we decrease further the temperature, this structure in the Lennard-Jones fluid change its shape according to this snapshot. But here in the Lennard-Jones with Yukawa tail, we cannot see very clear if this structure, if some kind of structure is formed. Now, for the lower temperature that we study, we can see that in the case of the Lennard-Jones with the long repulsions, there is a formation of some kind of cluster, elongated cluster, that also explain whole the system, the whole volume in the box. And this is the signature that we are looking for an arrested state. So we can establish that at this temperature that is much lower than in the case of the Lennard-Jones, we already see an arrested state. So to characterize these arrested states, we used the so-called localization length provided by the self-consistent generalized Langevin equation to determine if the final state is an ergodic or a non-ergodic one. So we use equation 3 that only demands and only requires the knowledge of the structure factor at the final time. And with this information and all the thermodynamics explored, we can determine the arrest phase diagram. So above these lines for the Lennard-Jones pure system, we found ergodic states. That means states that are not dynamically arrested. And below this line, we found the arrested states. Also, in the case of the Lennard-Jones with the Yukawa tail, we found the same states, but at lower temperature. So let me stop here. Mention the conclusions. The conclusion of this work is that we describe the similarities and difference of the equilibrium and non-equilibrium gels forming liquids in terms of the structural and dynamical properties. We found that the Lennard-Jones has marked structural and dynamical changes in their properties at certain temperature that is not seen in the case of the Lennard-Jones with a Yukawa tail. And in this case, we can use this information to determine the dynamic arrest lines. And for the first time, I think, for this kind of system with competing interaction, like the Lennard-Jones with the Yukawa tail. Well, the observation showing here are in good agreement with the predictions of the theory, and all seems to be consistent. So finally, let me acknowledge to the CONACYT, the Universidad Autónoma de San Luis Potosí, where this work was done when I was doing my postdoc under the supervision of Pedro Ramirez. And also thanks to Laboratorio Nacional de Ingeniería de la Materia Fuera de Equilibrio, and also thanks to you.
Okay, thank you for your presentation, Alexis. So now we continue with questions from the attendees or panelists. So we have only time for one question, please. If you have a question, raise your hand. So.
Victor.
Okay, Julio. Sorry, Julio. Sorry.
Hi, Alexis. How are you?
Hi, Julio.
I have many questions, but we don't have time for maybe one.
Yes,
perhaps two. Could you back at your slides? It's like a 9-8, where you're showing. By curiosity, it was a little bit curious. The radial distribution function, or like a factor structure.
Okay.
Yeah.
Why? Maybe here.
Yeah, I guess. No, I guess the next one. Yeah, in that. What is the reason that you find the first peak is very low in the case of Lennard-Jones plus Yukawa?
Yes.
The second one, it's bigger, but the third one, it's the biggest.
Oh, okay. You mean this first peak, second, and third,
yeah.
right?
Yeah.
Okay. Here, these first peaks, I can assume that is due to some kind of finite size effects, in the sense that we can. I cannot sure if this is a real effect or is something related with finite size effect due to the simulation limitation, for example. But it's important to mention that effectively the second and third peaks is almost with the same length or magnitude of the peak, no? So in this case, we can assume that there is two characteristic lengths in the system. The third is related with the short distance, the interaction between molecules, and the second peak here is related with the length characteristic of these elongated clusters. I can assure if this first peak that we see here at very low values of k is related with the size of all the cluster, because due to the periodic boundary condition, maybe it's an artifact that, as I already mentioned, related to the finite side effects.
Okay. And another quick question, Victor. Can I do it?
Okay.
Yes, please.
Okay. Could you go to the Alexis, where you're showing the structure for temperature 0.25 and 20, I guess, because I see that for 21 in the snapshots.
In the snapshot, okay.
Yes. Yes, in that. Back one. Could you back one? Exactly. So for the Lennard-Jones, in that case, I see a phase with the structure, but when you decrease the temperature, the structure disappears. Is less than why? I really, for me, it's strange. Maybe I haven't studied before health or glass transition or this kind of systems, but why, when you decrease the temperature, you destroy or you decrease the structure in the phase?
Well, first of all, these two simulations are doing independently. In one case, the start temperature is 1 and reduce the temperature to 1 and decrease to 0.35. And other simulation is the same condition, but with the final temperature 0.25. So yes, as you already mentioned, there are some loss of structure, but we can relate this because we are doing Brownian dynamic simulation. In this sense, there are some kind of energy provided by the fluid that can be used to rearrange the particles and form this kind of structure. So this formation that have in other temperatures is lost because now the energy is spared with other in other manner. No, in this sense, it's important to know how is the dynamic of the system. I mean, I think this is the reason why the structure changes dramatically between two temperatures.
So, but when you compare the potential energy between both phases, you see that the for lowest temperature is lowest the potential energy, or is highest?
No, it's lowest. It's lowest.
Lower. Okay. Well,
Okay.
thank you so much, Alexis.
Thank you to you.
Okay, thank you, Alexis. So we move to the next presentation. Okay, Dr. Tadek Emery, can you hear me?
Yes, I can hear you.
Oh, okay, how are you?
I'm doing fine, thank you. How are you doing?
Okay, fine, very good. So, okay, it's a pleasure to, let me see. You can, okay.
Can you see my screen?
Yes, of course.
Excellent.
Okay. It's a pleasure to present to Dr. Tadek Emersik from the Pritzker School of Molecular Engineer from University of Chicago. His presentation is titled Directed Cell Ensemble of Polymerizable Blue Phases Liquid Crystals. And so go ahead.
Okay, thank you for nice introduction. So hi everyone. Hi also to Mexico. I'm freezing here in Chicago. Here in Chicago, the weather is terrible. Yeah, so thanks to organizers to giving me this opportunity that I can share my work with you. So as been said, so my name is Tadej and I'm postdoc in Chicago under the supervisor of Professor Juan de Pablo. And today I'm gonna talk about the blue phase liquid crystals. And my talk gonna be from experimental point of view. So how my talk gonna be? So first in the introduction, I will briefly mention to you what blue phase liquid crystals are. After that, I will show you a few applications. After that, address two key issues that blue phases have. And these two key issues gonna automatically lead into the project that we are working on. And at the very end, I will summarize everything. So what blue phase liquid crystals are? So basically, these are chiral nematic liquid crystal material. So actually it goes for the thermotropic material that consists of elongated and isotropically shaped molecules that are twisting in a helical fashion, as we can see here. And the distance over which the molecules return back to the initial position is known as a pitch. And in case that the chirality in this system is very high, or in other words, that the pitch is very low, then at some certain point and some certain temperature, the system spontaneously goes into double twisted chiral nematic, as we can see here. So here we have twisting into two different directions that are perpendicular to each other. And this then forms these double twisted cylinders, as we can see here, or as we can see here. These double twisted cylinders spontaneously organize into crystalline structures, as we can see here, and this is known as a blue phase. And so these double twisted cylinders can organize either in a simple cubic crystalline structure known as blue phase 2, or in a body center cubic crystalline structure known as blue phase 1. Because these double twisted cylinders cannot tail the space, that's the reason why disclination lines appears, or defect lines that stabilize the structure itself. So about the blue phase, we know that blue phase exists in a very narrow temperature range between the chironemmatic phase and the isotropic phase. So here we are talking about 1 or 2 or 3 degrees C. Blue phases have fast optical response, high viscosity. As I mentioned, they form crystalline structure with a unit cell size that is pretty close to the visible light, so around 100 nanometers. And that makes them like a soft photonic crystals. They're generally polycrystalline. So as we can see here, so that means that they form many different domains of different colors. And we can see colors of blue phase because they have Bragg reflection in the visible region. And we can get the peak of the reflection light according to Bragg law if we know the unit cell size, if we know the reflection index, and if we know the Miller indices of the reflection plane. Because of all of these properties, blue phases are very promising candidates for different applications. And for example, they can be useful in the lasers, then for different kind of sensors. And also in 2008, Samsung already came out with a first blue phase prototype display. But even though that they are kind of promising candidates for the applications, they're still not as useful as they should be. And this is because of 2 key issues. So the first problem is polycrystalline structure that blue phase forms. And the second issue is this very narrow temperature range in which blue phases existed. So let's first take a look about the first issue, polycrystalline structure. So what is this the issue? This is the issue because that means polycrystalline structures, we have many small domains, and each of these domains reflects its own color or its own wavelength, right? And that in the end affect the final reflection wavelength. So reflectivity is not as high and as effective as we would like that should be. So we can overcome this problem with formation of single crystal. So here, let me mention that we typically explore liquid crystals in the liquid crystal chamber or liquid crystal cell. So just imagine we are facing 2 pieces of glasses together, and in between is liquid crystals. And continuum simulations of blue phase that are based on the Dao-De-Jane formalism. So these simulations show that we can form, so if we want to form the single crystals in this kind of confinement, then the system prefers that on one of the surface molecules of the liquid crystals are perpendicular to the surface, so that we have these alternative regions of where the molecules are perpendicular to the surface, and then where the molecules lay on the surface. And again, perpendicular to the surface, lay on the surface. So that means that the system prefers that on the surface, we have some kind of alternative regions between the homeotropic anchoring and planar anchoring. So in other words, from simulations, we can map the order parameter. So order parameter tell us how the liquid crystal molecules are ordered, right? So such a order parameter map provide actually blueprint for creating patterns of planar and homeotropy regions whose aim is to relieve the elastic distortion induced by the surface. And so, according to simulations, we made patterns. So in experiments, so these homeotropic and planar regions, dimensions, based on dimensions of the patterning that we are using, we can make theoretical predictions which blue phase with which lattice orientation gonna form single crystalline structure. And this is gonna be the one that has the minimum of the free energy. Let me mention that this different lattice orientation just means how we see the unit cell size regarding to the surface. And here at our university, our institute, people already showed a couple of years ago that if we have this pattern surface of homotropic and planar regions, if we place the blue phase on top of this pattern region, we really can form single crystals, as we can see here. So how those experiments are going? So on the pattern region, we inject the blue phase at the low temperature. At the low temperature, this liquid crystal or blue phase is actually chiral nematic, right? So cholesteric phase. And then we keep increasing the temperature. As I mentioned at the beginning, the system at some certain temperature gonna go into the blue phase, generally goes into the polydomains, but because we have patterns here on the region where the patterns are, single crystals form. So they showed this. And what these patterns actually are. So we make patterns on the silicon substrate in this way, that on the silicon substrate, we deposit first PMM mesobrush. So this is just some kind of polymer that dictates how the liquid crystal molecules want to behave on the surface. And we want that with the brush, we achieve homotropic anchoring. And then with the process of nanolithography or e-beam patterning, we make some kind of final product. So we make silicon substrate, as we can see here, with these alternative regions where the brush are. So here we have homotropic anchoring, so molecules are perpendicular to the surface. And then we have lines where the molecules lay on the surface, right? So planar anchoring. So with this e-beam lithography, nanolithography, we just remove the line, we just remove some certain area of brush, and we create this kind of alternative homotropic and planar anchoring. On top of that, we put another glass for the homotropic anchoring, and then in between, we inject the blue phase, and if everything is okay, then the system should form the single crystalline structure. This is just the image that show how patterns looks like with a scanning electron microscope. And yeah, so people showed this for one particular mixture, but after that we wanted to go a step further, and we asked ourselves, if these chemical patterns form single crystals in different blue phase mixtures, right? So to check this, we choose 3 different independent blue phase mixtures, as we can see here. So mixture 1, as we can see here, we have the nematic liquid crystals and chiral dopant. So basically these 2 are enough for the formation of blue phase. But we have also mesogens, monomer photoinitiator. This is for the purpose of polymerization that I will talk about later. Mixture 2 is similar to mixture 1, but here we have higher percentage of the nematic liquid crystal. And then the mixture 3 is pretty simple. We have the nematic liquid crystal and chiral dopant just in relation like 50-50. And so how our workflow actually looks like. So first, we take one of this mixture. We create a polydomains of the blue phase. And then we focus on one particular domain that we want that go into the single crystals later, right? So from this particular domain, we measure the reflection spectrum. We got the peak of the reflection light. And then according to the Bragg law, we can recalculate the unit cell size of this particular domain. Once we know this, we can use the numerical simulations because they can help us to reveal actually what are the right parameters, what are the right dimensions of homotropic and planar lines to achieve the single crystals, right? And so we know that the best is when the sum of homotropic and planar anchoring is pretty close to the unit cell size of the blue phase. So once we have this, then we inject the blue phase on top of these patterns, and the system should form the single crystals. So here are our results. So for mixture 1, for mixture 2, for mixture 3, what we can see. So we can see that in all 3 mixtures, we can very nicely form the single crystals of blue phase 2 with the lattice orientation 100. We can see different colors because we are dealing with different mixtures, and each of those mixtures has different unit cell size, right? Different unit cell size, according to Bragg law, means different reflection light. We can see that in all these 3 mixtures, we can also form blue phase 1 with lattice orientation 110, but in this case, we have granular structure. So in this case, we form monocrystalline structure. And as we can see here, with all of these, in all these cases, we can very nicely, we get the spectrum of colors. So all spectrums are very sharp and narrow. One thing here, so why we can form a very nice blue phase 2 and not blue phase 1? Yeah, we have very simple stripe line patterns, stripe-like patterns, and those are suitable for blue phase 2 because blue phase 2 has a simple cubic symmetry, right? But blue phase 1 has a body center cubic crystalline structure, and so this, it seems, is not as suitable for formation of single crystals. That's why we form a structure with that looks like a granula. And so with that, we confirm that with chemical patterns, we really can form single crystals of different blue phase mixtures. And we wanted to go a step further, and we wanted to address the second issue. So this is the narrow temperature range in which blue phases exist. So to check this, we choose one of the mixtures that I showed before. And this mesogens monomer photoinitiator is for the purpose of polymerization. So our purpose is that once we form the single crystals, we shine the sample with the UV light, and actually we want to freeze the system, right? And every molecule other than the nematic liquid crystal polymerize. So to do this, we did in this way that first, as you can see here, so we can see 4 setup of lines, right? For the formation of single crystal in blue phase that reflects the green lights. This is before polymerization. So once we reach this state, then we shine with light, the system freezes. Based on the diffraction patterns here, we can see that the blue phase with this lattice orientation remain the same. After that, we can play with the temperature up and down, so we can see that these single crystals, this single crystal structure actually remains more or less unchanged. We also measure the reflection spectrum. We can see that before polymerization, the spectrum is very narrow and sharp. After polymerization, the spectrum is a bit broader, but according to literature, it means that that the single crystalline structure was successful polymerized, and actually the structure remains, it was more or less, it remains the same as it was at the beginning. And this is how it looks like. This is just photo taken by phone. And here we can very nicely see this is the liquid crystal cells, right, or liquid crystal chamber. And here we can see very nicely how these 4 squares that we can see here, this is under the microscope, but this is just by the camera, we can very nicely see by eye actually what they looks like. So we can also polymerize blue phase single crystals, right? So not just form single crystals with different blue phases, we can also freeze them. So to summarize everything, we have unique approach how to form single crystals and monocrystals with these chemical patterns. They're like a generally applicable to different blue phases. We have numerical simulations that support us, that help us understanding what's going on, that we can get some parameters from the numerical simulations, right? And those parameters we use in the experiments. We shown that these chemical patterns are like generally applicable to different mixtures, and we can also freeze the system. So we have like a 2-in-1 actually. And so in the end, I just want to thanks to my colleagues, so to Dr. Kushal Bakchi, to Professor Martinez Gonzalez, Professor Shauli, Professor Paul Neely, and Professor Juan de Pablo. And I would like to thank you for your attention, and I'm happy to take any questions.
Okay, I would like to thank you for your presentation, Dr. Tadek. So if you have, yes, okay, now we continue from attendees or panelists, please raise your hand. So let me see. Okay, Julio.
Hey, hi Tadek. Thanks so
Julio.
much for your presentation, and results are very amazing. I have a couple of questions. One of them is, have you tried to study the same idea to use like the pattern lithography, but for a phase like the blue phase 3? I mean, try to, because in the blue phase 3, you have the problem that maybe it's difficult to keep the structure no? Like in the blue phase 2 or blue phase 1. How you think about that?
Yeah, well, not really, but there is one thing, right? So because blue phase 1 and blue phase 2 they have crystalline structure.
Yeah.
Blue phase 3 is like a amorphous state. So I don't really know what to expect in this case, if it's possible or not.
Well, there are some studies that maybe it's possible to have like a crystal, but it is not completely stable. So the thermal fluctuations, well, you know, in the blue phase 1 and blue phase 2, the range that you can find the phase is very, very narrow, no? Closest to, true. I don't know, 0.1, 0.2 Celsius. Okay, and the second one is when you put the blue phase about to the lithography. For example, if you want to apply this in order to make like a display, I mean, to change quickly, not the orientation of the molecules, maybe you can less like the transfer, no, the lattice, orientation of the lattice from one direction to other one, because from the simulation you can find like the substrate, no, induce to find a minimum on the global energy, and maybe it's hard for the system in order to apply like an electrical field or something like that, no, to move I mean, what is the possible application, no, of the single crystal of blue phase? Because maybe for the display it's not a good one.
Yeah, well, that's true. I think, yeah, they show that with the electric field you can switch between these single crystals from one phase to another phase. We also are planning to do this, yeah, like to check in this case. Applications of single crystals, that's the good question, yeah. You know, when it comes to questions,
I have to talk with Adrian. Because I know him and it's very good friend for to me.
Oh yeah,
so,
his simulations
this is
are very
but
awesome.
it's incredible because you are actually, I mean, you stabilize, no, with these patterns. This is the blue phase. That is an incredible result. But the second one is try to find a very good application, maybe for photonic devices. I mean, you can transport like a photons through to the blue phase, to the crystal of blue phase. No,
that's true.
That one, that I guess is a good application.
Yeah,
okay.
photonic crystal. Yeah, you're right. Thank you.
Thank you so much, Tadek.
Thank you, Julio.
Okay, so we have time for other questions. So someone else has a question, please raise your hand. Okay, Julio again, or someone else, please. Okay, no more questions. So thank you very much again, Tadek. So
thank you.
I hope to see you in Mexico. I mean, the next year.
I plan to visit it actually next year. So.
Of course. I know.
Excellent.
Okay, see you.
See you. Thank you.
Okay, thank you. Okay, so Dr. Sunao, can you hear me?
Yes, I can hear you.
Okay, how are you?
Yeah, fine, thank you.
Okay, good. Okay, good. So you can try to present it.
Okay, let me give some time. Okay. Here. Okay, can you see my first slide of my presentation? Hello?
Yes, I can see the presentation.
Okay, yes. So, okay, let me start my presentation. Okay, first, thank you very much for giving me a chance to talk about our recent study. And I'm very happy to be able to join your conference. So my name is Sunao Shimizu from Central Research Institute of Electric Power Industry, Japan. So today, I would like to talk about control of carrier density and controlling carrier density in materials and the modulation of physical property. So yes, okay. So it is very important to control the number of electron carriers in materials because the electron number determines properties of materials. So of course, even the number of electron carriers in the material is very low, the material is insulator. So when we increase the number of carrier density or number of carriers, the material becomes semiconductors and then metal. So in metallic region, so we observe, for example, in superconductivity or spintronics property, and in semiconducting region, we also observe interesting properties such as PN junction, solar cell, light emitting diode, or quantum Hall effect, or something like that. So this means that, so in order to investigate the novel functions of materials, the controlling carrier density is very important. So one of such interesting property of solid is some electric effect or Seebeck effect. So Seebeck effect is a property which can convert waste heat into electricity. Now this is very traditional and classic phenomena, and we can generate microwatt or milliwatt energy very easily. So this phenomena or the some electric energy conversion is very stable. Some electric module is very stable because it has no moving parts. So that it has been working for several decades, for example, in spacecraft. So in order to, in addition to such the uses in outer space, so recently we think that we will use a lot of sensors for the IoT, so that some electric power generation or modules has attracted renewed attention as a possible power source for IoT sensors. So then in order to find or investigate novel some electric materials, so it is important to control carrier densities. The reason is very simple. So the property of some electric material is evaluated as ZT value or power factor S squared sigma. The S is Seebeck coefficient and sigma is electrical conductivity. Here kappa is some thermal conductivity and T is temperature. So this ZT or power factor changes drastically with changing carrier density. So this is a schematic figure. So when we increase carrier density of materials, the Seebeck effect decreases like this gradually. And on the other hand, the electrical conductivity increases like this, so that the power factor S squared sigma shows a maximum at some carrier density. So that when we investigate some electric materials or some electric properties, so we have to systematically control carrier density. So that usually it is not so easy, or it is very difficult to control carrier density systematically in a material. So then, so in order to do so, we have focused on the ionic liquid gating technique. So here I want to briefly introduce the electric double layer gating. So the left figure is a very simple schematic picture of electrochemical cell in which we put ionic liquid or liquid electrolyte and 2 electrodes here. So when we apply some voltage between these 2 electrodes, so of course the electric field is applied to ions. Then the ions, I mean cations or anions, moved to different directions. And finally, we observe the formation of the electric double layer on the surface of electrode. So it is known that this electric double layer is very, very narrow or thin, so that the electric double layer has a very big capacitance. So that we expect that there is a lot of electron carriers on the surface of electrodes. So this is actually the mechanism of the supercapacitor. So we have applied this electric double layer to the field effect transistor. So this is the left figure is the schematic picture of the conventional field effect transistor. So here, this is G means gate electrode, and the bottom one is a semiconductor that we want to investigate the physical property, and this is a solid gate insulator. So when we apply some voltage between a gate electrode and semiconductor, so we can accumulate some electron carriers on the surface of semiconductor here, like this. So, but what happens when we change this solid gate insulator to liquid? So the answer is very simple. So when we apply gate voltage between gate electrode and semiconductor, so we observe the formation of the electric double layer on the surface, and due to the high capacitance of the electric double layer, so we can accumulate a very large amount of charge carriers on the surface of semiconductor. So, and actually, in this electric double layer transistor configuration, the charge carriers accumulated on surface is much larger than conventional solid gate FET. So this means that this electric double layer gating technique is very effective to control carrier density and investigate physical and chemical properties of materials. So today I want to introduce two topics using this electrolyte gating technique. The first topic is the electrostatic carrier doping in carbon nanotubes, carbon nanotube thin films. And the second topic is electrochemical doping in tungsten oxide thin film. Okay, so let's go to the first topic. So here, we fabricated electric double layer transistor device based on carbon nanotube for some electric measurement. So this is the schematic picture of the carbon nanotube transistor device. So this is the glass substrate, and we put carbon nanotube thin film, and we put ion gel or ionic liquid to cover carbon nanotube thin film here. And also we put gate electrode on top of it. So by changing the gate voltage here, so we can control the carrier density of carbon nanotubes. And actually, so let's look at the inside the carbon nanotube thin film. So we are in the carbon nanotube thin film, there are a lot of carbon nanotubes or bundles of carbon nanotubes, and each bundle or each carbon nanotube are surrounded by ions, ionic liquid like this. So we can control carrier density by changing gate voltage VG. So here we show some experimental data. So this graph shows the gate voltage dependence of the resistance of carbon nanotube thin film. So when we increase gate voltage, the resistance of carbon nanotube increases and shows the maximum and starts to decrease like this. So this means that when we apply negative gate voltage, so the carriers in the carbon nanotube thin film is whole. And when we apply positive gate bias, the carriers is electrons. And here, this point is charge neutral point at which the film energy or chemical potential is just located at the middle of the conduction band edge and valence band edge. So we also measured the Zerbeck effect simultaneously. So result is like this. So in the hole doped region, the Zerbeck coefficient is positive, and in the negative electron doped region, the Zerbeck effect is negative. So and please note that here at charge neutral point, the Zerbeck coefficient is 0 because the contribution from holes and carriers are cancelled out completely. So this data clearly shows us that we can control the film energy or carrier density of materials systematically by using electric double layer gating technique. So yeah, I want to focus on the gate voltage dependence of physical properties. So the left upper figure shows the conductivity or conductance of the carbon natural thin film as a function of gate voltage. So when we reduce the gate voltage, I mean, when we increase the number of hole carriers in the carbon nanotube, so we observe the enhancement of conductivity here and here, conductivity, and also we observe some change of the slope here and here. So in order to see it more clearly, we took the derivative and we also observed the two peaks here and here. So those peaks correspond to the southbound edge in the carbon nanotube thin film. So here, our light figure shows the schematic picture of the density of states in carbon nanotube. So when we decrease the gate voltage, the film energy shifts from the charge neutral point to lower energy region. And when the film energy passes the edge of the southbound, we observe the change of the conductivity here, like this, here and here. So we also observed this kind of anomalies in the Zebek effect. So this is the first southbound edge, and this is the second southbound edge. So at the first southbound edge, we observed the large value of the Zebek coefficient, and second southbound edge, we observed some anomalies or kink structure here. So this is because the Zebek coefficient is related to the density of states also. This equation, we can find this equation in the textbook of the solid state physics, and which is called motivation. So according to this equation, the Zebek coefficient is related to the energy derivative of conductivity or density of states. So we can clearly see those anomalies in our measurements. So we measured the Zebek effect and also resistivity as a function of gate voltage or carrier density, so we can estimate power factors, which is very important, the property of some materials. So this is a result, the power factor as a function of gate voltage. So when we reduce gate voltage, so the power factor increased like this, and then finally show the maximum in second southbound region. So we successfully optimized the power factor in carbon natural thin film, and which is very difficult to be achieved by a conventional bulk chemical doping technique, because so it is very difficult to dope or inject a lot of whole carriers like this. So we can apply this technique to other materials also. So as I mentioned at the beginning of this presentation, so we can dope carriers by using electric double layer technique, electric double layer like this. So when we apply gate voltage here between gate electrode and semiconductor, the electric double layer is formed, and due to the formation of the electric double layer, we can accumulate a lot of charge carriers on the surface of semiconductor. But by using the same configuration, we can dope electrons in the bulk of semiconductors. So the mechanism is shown in the right figure. So due to the very large electric field at the interface, so we can integrate some small ions, for example, a proton, lithium ions, or potassium ions from the liquid to the bulk of semiconductor. And also, if the target semiconductor is oxide, we can remove oxygen from the semiconductor. Okay, anyway, by using this integration or removal of oxygen, we can dope electrons into the bulk of semiconductors. So by using this technique, so we control the physical property of tungsten oxide. So this figure is the crystal structure of tungsten oxide. So as you can see here, there is a lot of the void space, so that probably it is easy to integrate some ions or remove oxygens from this structure. And this picture is a schematic picture of the device structure. And here we put a tungsten oxide thin film. And here, this is a gate electrode. And we put ionic liquid to cover both tungsten oxide and a gate electrode. And by changing gate voltage, we can control the carrier density in the tungsten oxide thin film. So this left figure shows the transfer curve. So when we apply gate voltage, positive gate voltage, the drain source current increased. This means that the resistance decreased. So the right figure shows the temperature dependence of resistance of the tungsten oxide thin film. So when we apply 0 gate voltage, this material is completely insulator. But when we apply positive gate voltage, the resistance decreased gradually. And finally, it shows a flat metallic temperature dependence of resistance. And at the same time, we also measured the Zeebeck coefficient like this. So yeah, please look at the right figure. So as you can see here, the Zeebeck coefficient also changed gradually with changing gate voltage. So this means that we can systematically control the carrier density and also a physical property of semiconductor by using the electrolyte gating technique. So we also now we measured the Zeebeck coefficient and the resistivity of this material. We can estimate power factor. So the result is here. Now this shows the power factor S square sigma as a function of temperature and as a function and also gate voltage. So when please look at the data around room temperature. So when we increase gate voltage, the power factor gradually increased, and then I showed the maximum at around 3 volt, and then started to decrease. So this data shows that we can successfully maximize or optimize the power factor of tungsten oxide thin film. So in this presentation, I introduced that we can control the carrier density of materials by using electric double layer or electric double layer gating technique. And we can we can control, we can dope carriers systematically on the surface of semiconducting materials, or we can dope carriers into the bulk of semiconductors by utilizing electrical chemical reaction. And also we introduced the 2 examples. One is carbon nanotube and the other one is tungsten oxide. So which shows that the optimization of some electric properties. And finally, so this electric double layer gating is a very versatile technique to control physical property of materials. So today we introduced some properties, but this technique can be applied to other interesting properties such as superconductivity or magnetic orders. And this is a review article, so that if you have some interest on the electrolyte gating technique, please see these articles. And thank you very much for your attention. And this is the end of my presentation.
Okay, Dr. Tsunao, thank you for your presentation. So
Yes.
I would like to thank you for accepting the invitation as an invited speaker. So let me see, Dr. Tsunao is from the Central Research Institute of Electric Power Industry in Japan. So I have a question. So Dr. Tsunao, what time is it now over there? In this
You mean time in Japan?
Yes.
Yeah, yes. Now it is 7:30 in the morning.
Okay, Tuesday. Okay.
Yeah.
Okay.
No. Tuesday. Yes, Tuesday morning.
Tuesday morning. Okay. Good. Okay. So now we continue with questions from attendees or panelists. If you have a question, please raise your hand, please. Raise your hand. Okay. So do you have a question, Ivan?
Yes. Your video was frozen a little bit. Yes, thank you, Victor. Nice to meet you, Tsunao.
Nice to see you.
And congratulations for your presentation. In one of the applications that you have shown us, you mentioned that you use ionic liquids. Is that right?
Yeah, right. I used Gigit.
And is there any difference, for example, if you use multivalent ions instead of ionic liquids, or is it crucial to use ionic liquids for this effect that you have shown us?
Oh, okay. You mean the difference between using ionic liquid or, for example, lithium salt or something like that?
Yes.
Yes. The answer is actually we can use both ionic liquid and also the polymer and lithium salt. So sometimes we use lithium salt and sometimes we use ionic liquid. The good point to use ionic liquid for the electrical device is that ionic liquid is very stable. Probably the chemical window of the ionic liquid is very large compared to lithium salt sometimes. So that, yeah, in order to, how can I say, in order to have a very big chemical window, so we sometimes use ionic liquid. And also, when I want to do intercalation of lithium salt or potassium into the semiconductors, then we use a lithium salt.
I see. And thank you. And do you find some effects regarding pH?
pH.
Yes.
I haven't cared about it.
Okay, so maybe it's not very relevant for your application.
Yeah, so yeah, that is probably yes, but at the same time, I don't know about it because I'm physicist, so that I haven't cared about pH so much. Yeah, that's, yeah, of course, as you said, sometimes it is very important to carefully check pH and the effect of the pH into our device.
I see. Okay, well, thank you very much.
Yeah, thank you very much.
Okay, thank you. So someone else has a question? Please raise your hand. Attendees. Please. Panelists. Okay. Let me see. Okay. No one else, I think. Okay. No more questions, Dr. Sunao. So yes. Again, thank you for your presentation. So thanks.
Yeah, thank you very much.
Okay, thank you. See you.
See you next time.
Okay, thank you. So we will back tomorrow with the presentation of Rosana del Castillo. If the panelists have an announcement, please let us know. No? I don't know, Eric, Ivan, Francisco.
Maybe it's a good idea to invite everybody to the posters.
Oh, okay. If you want.
I do not remember that there are further announcements.
Okay, I'm not sure. Let me see. Francisco is in charge. Oh, Eric. I'm not sure. I'm not sure, Ivan. Okay. So thank you very much for all the attendees, our panelists. So we will back tomorrow with the presentation of Rosana del Castillo. So thank you and see you soon. Thanks.
Thank you. See you tomorrow.
See you. Thanks.
Thank you, Victor.
Okay. Bye.
Bye, everybody.